You think the universe will last trillions upon trillions of years, stars burning, galaxies rotating, civilization continuing for timescales so vast they might as well be forever. But what if I told you the universe could end tomorrow? What if I told you there is a probability, small but non-zero, that as you watch this video, the entire universe is being destroyed from the inside out at the speed of light? What if everything, including you, could cease to exist in the next instant? Prepare to learn why the universe is far more fragile than anyone admits. The universe is 13.8 billion years old. Stars will continue to burn for trillions of years. The sun has 5 billion years left. Red dwarf stars will last 100 trillion years. The universe appears stable, eternal, built to last. This gives us a sense of cosmic permanence. The universe has been here forever in human terms, and it will be here forever in human terms. We have time, vast amounts of time, deep time measured in time scales that make geological eras seem like eye blinks. But this sense of permanence is an illusion. The universe could end at any moment, not through some external catastrophe, not through heat death after countless trillions of years, but through an internal instability that has been lurking since the moment of the Big Bang, a flaw in the fabric of reality itself that could trigger at any instant and destroy everything that exists in a wave of annihilation expanding at the speed of light. This is not science fiction. This is not speculation. This is a prediction from quantum field theory combined with our observations of the universe. And it means that every second the universe continues to exist is something we should not take for granted. Let me explain what vacuum decay is and why it threatens everything. The vacuum of empty space is not truly empty in quantum field theory. It is the lowest energy state of quantum fields that permeate all of reality. These fields exist everywhere, filling all of space, even regions that contain no particles or matter. The vacuum is the configuration of these fields when they are in their ground state, their lowest possible energy. But here is the problem. What if the vacuum we live in is not the true vacuum? What if the ground state we exist in is not actually the lowest energy state? What if there is a lower energy configuration of the quantum fields that the universe has not yet found? This is called a false vacuum, a metastable state that appears stable but is not the true minimum energy. Think of a ball sitting in a shallow valley on the side of a mountain. The ball is stable in the valley. It will sit there indefinitely. But if you give it a push, if you provide enough energy to get it over the lip of the valley, it will roll down the mountain to a much deeper valley at the base. The shallow valley was a local minimum. The deep valley at the base is the global minimum. The vacuum of our universe might be like that ball in the shallow valley. Stable for now, but not truly stable. And quantum mechanics provides a mechanism for the ball to escape the valley, even without being pushed. Quantum tunneling. In quantum mechanics, particles can pass through energy barriers they classically could not overcome. An electron does not need enough energy to climb over a barrier. It can simply appear on the other side through quantum tunneling. The probability is often small, but it is never zero. Everything in quantum mechanics that is not forbidden has some probability of happening. The vacuum can quantum tunnel, a small region of space through a random quantum fluctuation, can tunnel from the false vacuum state to the true vacuum state. This creates a bubble of true vacuum in a sea of false vacuum. And once this bubble forms, it grows. The boundary of the bubble expands at the speed of light, converting false vacuum to true vacuum as it propagates. Inside the bubble, the laws of physics are different. The vacuum energy is lower. The masses of particles are different. The strengths of fundamental forces are different. The constants of nature that we rely on are not constant anymore. Chemistry does not work the same way. Atoms may not be stable. Life is impossible. The expanding bubble does not just change the laws of physics. It destroys everything in its path. As the bubble wall passes through you, The particles that make up your body are reconfigured according to the new physics. Most configurations are not compatible with the complex structures needed for life or even for stable matter. You are not converted to a different form. You are annihilated. The information that constituted you is lost. The bubble expands at the speed of light. You cannot see it coming. Light from the approaching bubble wall cannot reach you before the wall itself arrives because the wall is moving at light speed. There is no warning, no chance to escape. One moment you exist, the next moment you are gone, replaced by a region of true vacuum with different physics. And once one bubble nucleates, it does not stop. The bubble grows without limit, eventually consuming the entire observable universe. Every galaxy, every star, every planet, every living thing, every structure that exists is obliterated and replaced by true vacuum. The universe as we know it ends, not in heat death after trillions of years, not in a big crunch, but in an expanding wave of annihilation that sterilizes the cosmos completely. How likely is this? That depends on several factors we do not know with certainty, but we can estimate. The probability of vacuum decay depends on the height and width of the energy barrier between the false vacuum and true vacuum. A tall, wide barrier makes tunneling very unlikely. A short, narrow barrier makes tunneling more probable. The exact shape of this potential energy landscape depends on the properties of the quantum fields that fill space, particularly the Higgs field. The Higgs field gives mass to particles through their interactions with it. The Higgs field has a potential energy function that determines its ground state. Measurements from the Large Hadron Collider have determined the mass of the Higgs boson very precisely, about 125 GeV. And this mass, combined with other measurements, allows physicists to calculate the shape of the Higgs potential at high energies. The calculations show something disturbing. With the measured Higgs mass and the measured top quark mass, the Higgs potential appears to have a second minimum at very high field values, a deeper minimum than the one we currently occupy. Our vacuum is metastable. We are living in a false vacuum. The barrier between our vacuum and the true vacuum is high and wide. This means quantum tunneling is incredibly unlikely. The probability per unit volume per unit time is extraordinarily small. Calculations suggest the decay rate is so low that the expected lifetime of the false vacuum is vastly longer than the current age of the universe. Perhaps 10 to the power of several hundred years or more. This sounds safe. A lifetime much longer than the age of the universe means we should not worry. But there are several problems with this reassurance. First, the calculation depends on parameters that we do not know with perfect precision. Small changes in the Higgs mass or the top quark mass or other parameters could dramatically change the decay rate. If the true minimum is closer than we think, or if the barrier is narrower than we calculate, the decay could happen much sooner. The uncertainty in our measurements translates to uncertainty in the decay timescale spanning many orders of magnitude. Second, the probability might be small per unit volume per unit time, but the universe is enormous. The observable universe contains about 10 to the 80 particles. The volume is vast. Even an incredibly unlikely event becomes plausible when you have an entire universe worth of opportunities for it to happen. Somewhere in the vast cosmos, a random quantum fluctuation could nucleate a true vacuum bubble right now. Third, high-energy processes might trigger vacuum decay. The barrier between false and true vacuum might be crossable not just through quantum tunneling, but through classical transition if enough energy is concentrated in one place. Collisions at particle accelerators, black hole evaporations, violent astrophysical events could potentially provide the energy needed to push the Higgs field over the barrier. The Large Hadron Collider collides protons at energies of several TeV, far below the Planck scale where quantum gravity becomes important, but still at energies never before achieved in controlled experiments. Could these collisions trigger vacuum decay? Physicists have studied this carefully and concluded the risk is negligible. The cosmic rays that constantly bombard Earth have energies far higher than anything the LHC produces. If high-energy collisions could trigger vacuum decay, cosmic rays would have done it already. The fact that the universe still exists after billions of years of cosmic ray bombardment suggests we are safe from LHC-induced vacuum decay. But this argument assumes that concentrated laboratory energies behave the same as dispersed cosmic ray energies. It assumes that the geometry and quantum state of the collisions do not matter. These are reasonable assumptions, but not certainties. There remains a tiny, tiny possibility that something about our experiments could trigger a transition we would not see in nature. Fourth, and most troubling, we do not know if our vacuum is stable, metastable, or unstable. The calculations showing metastability assume we know all the relevant physics up to the Planck scale, but we do not. There could be new particles, new fields, new interactions at high energies that we have not discovered. These could change the shape of the potential dramatically. We are extrapolating our known physics across 16 orders of magnitude in energy from LHC energies up to the Planck scale. That is an enormous extrapolation. Any new physics in that range could alter the conclusion. String theory suggests the vacuum structure of the universe might be far more complex than we imagine. The string theory landscape contains perhaps 10 to the power of 500 different possible vacuum states. Each one has different values for the fundamental constants, different particle masses, different forces. Our universe exists in one of these vacua, but are we in the true minimum, or are we in a metastable state that could decay to a lower energy vacuum? String theory does not give a definite answer. The landscape is so vast that we cannot calculate the properties of most vacua. We do not know where our vacuum sits in this landscape. We do not know if there are lower energy vacua nearby that we could tunnel to. The string theory landscape, if real, makes the vacuum decay problem potentially worse because it increases the number of possible destinations for a decay. Eternal inflation adds another layer of concern. In eternal inflation, different regions of the multiverse are in different vacuum states. Bubbles of different vacua nucleate in the eternally inflating space and expand. Our observable universe is one such bubble. But other bubbles with different physics are constantly forming. Some of those bubbles might have lower vacuum energy than ours. And if a lower energy bubble forms near us, its boundary could propagate into our bubble, converting our vacuum to the lower energy state. We would not see it coming. The boundary between vacuum bubbles expands at the speed of light. There is no causal connection between the interior of our bubble and the exterior until the boundary arrives. We cannot detect the approaching bubble. We cannot prepare. We cannot escape. One moment we exist in our vacuum. The next moment we exist in a different vacuum with different physics. And almost certainly that transition is not compatible with our survival. How soon could this happen? The honest answer is we do not know. It could happen in the next second. It could happen in 10 to the power of 500 years. Both are possible. The probability is non-zero at all times. Some physicists have tried to place observational constraints on vacuum decay rates. If vacuum decay were happening frequently in our cosmic neighborhood, we would see evidence. We would observe regions of space with different physics. We would see bubble walls propagating through the universe. We do not see this. Our universe appears homogeneous on large scales. The laws of physics appear the same everywhere we look. This suggests vacuum decay, if possible, is rare. But absence of evidence is not evidence of absence. Just because we have not observed vacuum decay does not mean it is not happening elsewhere or about to happen here. The observable universe is finite. We can only see light that has had time to reach us since the Big Bang. A vacuum decay bubble could have nucleated 1 billion light years away 1 million years ago, and we would not know yet. The light from the destruction has not reached us. The bubble itself, expanding at light speed, has not reached us, but it is coming. Alan Guth and others have calculated the survival probability of our vacuum. Under certain assumptions about the decay rate, they find that the probability our vacuum survives for another n years decreases exponentially with n. The longer you wait, the more likely it becomes that somewhere in the vast universe a bubble has nucleated, and once one bubble nucleates, it grows without bound. This gives the universe a kind of half-life, not a definite lifespan, but a statistical distribution. There is a characteristic time scale over which the probability of survival drops significantly. If that time scale is longer than trillions of years, we might not worry. But if it is shorter, if it is comparable to the current age of the universe, then we are living on borrowed time. Every moment could be our last. Could we survive vacuum decay? Could we develop technology to prevent it or escape it? The answer is almost certainly no. Vacuum decay is not an engineering problem. It is a fundamental instability in the structure of space-time itself. You cannot build a wall against it because the wall itself is made of particles whose properties are defined by the vacuum state. When the vacuum changes, the wall ceases to exist. You cannot outrun it because it travels at light speed. You cannot detect it before it arrives because no information can outrun light. Even if you somehow knew a bubble was approaching, there is nowhere to go. The bubble eventually consumes the entire universe. You might escape one bubble only to be caught by another nucleated elsewhere. The only possible escape would be to leave the universe entirely, to enter a different vacuum state that is more stable, but we have no idea how to do that. We have no technology that could manipulate vacuum states. We barely understand what vacuum states are. Some speculative ideas involve creating artificial stable regions using enormous energies. Perhaps a sufficiently advanced civilization could stabilize their local vacuum by creating an energy density high enough to change the effective potential. But this would require energies comparable to the Planck scale, concentrated in macroscopic regions. We cannot do this. It might be fundamentally impossible, and even if possible, it would only protect a tiny region. The rest of the universe would still be doomed. The anthropic principle offers a strange kind of reassurance. If the vacuum decay rate were very high, the universe would have decayed long ago, and we would not be here to worry about it. The fact that we exist and observe a stable universe that has lasted 13.8 billion years tells us the decay rate must be low enough to allow our existence. This is not a calculation. It is an observation selection effect. We can only find ourselves in a universe that has not yet decayed. But the anthropic principle does not tell us how much longer we have. It only tells us the vacuum has been stable until now. It says nothing about the future. The decay could happen tomorrow, and that would still be consistent with the anthropic constraint because we are here now. There is also the quantum immortality interpretation, which some people invoke. In the many worlds interpretation of quantum mechanics, every quantum event branches reality into multiple outcomes. When vacuum decay occurs, there might be branches where it did not occur. Your consciousness continues only in branches where you survive. So from your subjective perspective, you never experience vacuum decay. You always find yourself in branches where the universe continues. This is not comforting. First, the many worlds interpretation is controversial and might not be correct. Second, even if correct, it does not mean your branch survives. It means some version of you in some branch survives, while countless other versions are destroyed. The version of you reading this now has no special protection. Third, quantum immortality leads to bizarre conclusions about subjective probability that most physicists reject. The real situation is this. We live in a universe that might be in a false vacuum. If so, it could decay at any moment through quantum tunneling. The probability is small but non-zero. There is nothing we can do to prevent it. There is no way to detect it before it happens. No escape is possible. The universe and everything in it could end tomorrow, or in 1 trillion years, or never if we are lucky enough to be in a truly stable vacuum. This uncertainty should change how we think about the future. We plan for the long term. We worry about climate change, asteroid impacts, the far future of civilization. These are reasonable concerns, but they all assume the universe is stable. They assume the laws of physics will continue to work the way they do now. Vacuum decay could make all of these concerns irrelevant, not gradually over geological time, instantly with no warning for reasons beyond our control or even our understanding. Does this mean we should despair? Should we abandon long-term planning because the universe could end at any moment? No. The probability is small. Almost certainly the universe is stable enough to last far longer than human civilization or even biological life will exist. We should plan for the future we can reasonably expect, but we should also maintain intellectual humility about what we know and what we do not know. The universe is more fragile than it appears. The stability we observe is not guaranteed by any fundamental principle. It is a contingent fact about the particular vacuum state we happen to inhabit. And there is something profound in this uncertainty. The universe does not owe us stability. The laws of physics do not promise permanence. Every moment of existence, every structure that forms, every thought that occurs, is a temporary configuration in a vast landscape of possibilities. We exist in a narrow range of conditions that permit complexity. Those conditions could change. The fact that they have not yet changed is fortunate, but fortune is not physics. The universe could end sooner than you think, much sooner. The time scale for vacuum decay could be shorter than current calculations suggest. New physics at high energies could destabilize our vacuum. A random quantum fluctuation in some distant part of the universe could nucleate a bubble that will eventually reach us. We would never know until the bubble wall arrives moving at light speed, erasing everything. This is not meant to frighten you. This is meant to give you perspective. The universe is not a static, eternal backdrop. It is a dynamical quantum system in a particular configuration that happens to allow your existence. That configuration is probably stable for a long time, but probably is not certainly. And the difference between probably and certainly is the difference between living in a secure universe and living in a universe that could end in the next instant. Every second you exist is a gift, not because some entity is giving it to you, but because the quantum fields that fill space have not yet found a lower energy state, because the probability of vacuum decay in your region has not yet realized, because the universe for now continues, and that is all we ever had, all we ever will have, a present moment in a universe that may or may not have a future. Make the most of it, because sooner than you think might be sooner than you can possibly imagine.